students. I hope everybody can hear me okay. Sometimes I have problems with the sound, they say. I have no idea why, because I can always hear the videos quite well, so I don't know. Anyways, we're going to be talking about the Higgs today, Higgs boson, okay? And the issue there is that, you know, what is the Higgs boson? Is there such a particle? But before I can get there, I'm going to talk about a little anecdote that I'd like to share with you and gives you a little glimpse of how the editing world, the so-called scientific publishing world works behind the scenes. And turns out that about, what was it, 2002, 2003, about 24 years ago, thereabouts, I submitted a paper to Science Magazine. And they politely rejected it, saying that it was more appropriate for philosophy than for physics. Okay, so I submitted it to a philosophy magazine after that. And they said, well, who approved it? I mean, over there in physics. It was like, you know, they were playing ping pong with me. These guys won't publish it because it's not, they consider it not to be physics. And the other folks are saying, well, did you get the approval of the physicists to be able to publish this in philosophy, in, you know, metaphysics, that kind of thing? And so I realized that, you know, no one was going to publish this. In fact, if any peer reviewer from the establishment looked at it, they would have rejected it right off the hand because several reasons. A couple people have told me that they don't even look at classical mechanics anymore. Mine was tending to classical mechanics. It was trying to give an explanation for the atom and for light. That's one issue, but it would destroy everything that they were educated on in high school and in college, you know, about particles and waves, because that's what I was destroying, particles and waves. And so it's kind of hard to send a, you know, a paper to a religious organization, start your paper by saying, oh, by the way, God doesn't exist. You know, the chances of getting published there are, you know. So I finally ended up sending it to a dissident organization known as Outrun, and in Canada, and they reviewed it, and three judge panel, whatever, reviewed it, and to my surprise, they approved it for publication. And I was surprised because, you know, I don't know if they read it, if they just rubber stamped it, if they understood it. I don't know to this day. But the issue is that the person, it was supposed to go into a book. And this is the book. It's known as What is the Electron? Okay? Because that's what I was explaining, what the electron is, what an atom looks like. Okay? And of course, what happened was this fellow, the editor, a fellow by the name of Simulik, he took over 2 years to get his act together. He just took a long time, and it was very frustrating even for the people at Apeiron. And the issue is that 2 months before publication, a month and a half, 2 months thereabouts, he asked that I withdraw my submission. And the reason he asked for a withdrawal became quite apparent. You know, if you looked at the papers that are published in that book, and here's the book, okay? This is what the book looks like. What is the Electron? By Simulik there. And what was the issue? The issue is that all these people, including Simulik, you know, this is what they published. They published equations, you know. Volume is low. Aha. Let's see if I can raise it a little bit. I don't know what to do about this anymore. Give me a second here. I'm going to try to raise it. Okay, you should be able to hear me better now. Let me know otherwise. Is it better? Got any better yet? Okay. Well, I hope you can hear me. Anyways, the issue is that these people were publishing uh, equations, and here's another paper, okay, from that same book. You can see what the person is. Okay, thank you. Um, you can see what they were publishing. They were publishing equations, okay. And here's another one just to show you, okay. Okay, you can see it there. Uh, just a bunch of equations. What was the name of the title of the book? It's What is the Electron? And these people are publishing, this stuff, equations. And this is the title of the book. What is the electron? Now, I'll give you an analogy just to show you how how this shocked me. You go to the Mars, you go to see the LGM, the little green men, or you go to the land of the Klingons, and in your talk with them, you mentioned the word table. And so they ask you, what is a table? And you say, well, the radius is 1 meter. Um, it has a charge of 1.6 times 10 to the minus 19 coulombs. It has a spin of minus half. We don't know really what spin is, some kind of angular momentum, but it's a minus half for the table. And it weighs a ton or whatever. I mean, is that what a table is? Have you understood what a table is? You would think that the least they would do is, point to a table, which is what I did. This is what I wrote in my paper. Okay, I put some kindergarten stuff, and this, I guess, was out of tune with what everybody else out there, wrote and published. Give me a second here. So this is this is some stuff that these people didn't understand. They said, "What's he doing? What what is this? A picture in a in a magazine, in a physics magazine?" Yeah, they had no pictures. They had no pictures. Everybody just wrote equations. And out of 17 papers, I was the only one who had a picture in there of what the electron is. So I have a problem with all these people, who ask a question. They don't even know what they're asking. What are you asking? What are you trying to find out? I mean, if you ask, what is the electron, and you give me a bunch of equations, either you didn't understand the question, your own question, because they posed the question, or they don't realize what they're answering. They're completely out of touch. And it brings you back to, this issue of what is physics about? I mean, is physics about equations? Is that what physics is? I mean, that's what it's become, and it's primarily because of these two fellows here. Galileo said, I think that in the discussion of natural problems, we ought to begin with what? Experiments and demonstrations. And he said, mathematics is the language in which God has written the universe. And Newton said more or less the same thing. He was born when the other guy died, more or less. And, several decades later he said, that for the qualities of bodies are only known to us by experiments. Absolutely not, Newton. There are qualities of bodies and bodies themselves that are not known to us by experiments. You are unable to see or touch them. And universal is such as universally agree with experiments. And yeah, you won't be able to see the mediators of light and gravity in any experiment. So you can run your head, to infinity, and you'll never, with an experiment, show me what is the mediator of light or the mediator of gravity. And that's why they use words such as wave and field and energy, because they cannot understand what's in there in that physical world that they cannot see. And then again, he says, the moderns referring to his age, right, his colleagues, have endeavored to subject this phenomena of nature to the laws of what? Of mathematics. I have in this treatise cultivated mathematics so far as it regards philosophy. And so all these people, they impose this notion that science is about experiments, measurement, right? Followed by measurement, observation, and eventually an equation. And, none of that belongs to science or physics. All that is description. You have described something. And they think that a description is sufficient. It's like, I describe a chair and I get an oval because, I described the chair. And they forgot to point to the chair. So I don't know what they're describing because I've never seen the chair. And that's what they do with the atom, with the electron, with all these things. They've never seen one. And they just describe it mathematically and they say, okay, I'm done. And so they never visualized, the invisible world of Mother Nature, the untouchable. They think they can go to run an experiment, be able to see and touch, and that's not the case. The only way you can touch and see or touch, for that matter, right? Mother Nature's mediators is with the mind. Okay, that's the only way. You have to lay back and make an assumption, supposition of what could be in that world of hers that you cannot see or touch, that you cannot discover through an experiment in the lab or in the field. And you just have to visualize, you have to imagine, you have to try to rationalize what she is doing in that invisible world. So a lot of these people, they want some hands-on proof. Let me go to a lab and prove to see if this is the case or not. You can't do that with gravity for sure, light, magnetism. No, you can't do that. Turns out that, you have all these people, again, they went with experiments and so on, Galileo there, Newton, and none of that changed in the last 400 years. Here you have Bohr, Niels Bohr, and he had a very funny way of saying things, a little violent, but he said it like he meant it, right? And you have people like Einstein, they expected to have some rationality, understanding of how the universe works, a physical interpretation. And so he would say, God does not play dice. And Niels would say stuff like this to people who said, hey, you're trying to get some understanding here. Are you crazy? Shut up and calculate. It's all math. In other words, none of it has to do with interpretation and understanding. And so today you have these people that say, we can't find any meaning. Yeah, no kid. I don't blame you. You can't find any meaning because, you are not interested in meaning. Or like the people in science said, oh, meaning is not part of physics. Meaning is part of, philosophy. And then the philosophers say, well, did you get your cue from the physics? Did they approve it? so you keep running around in circles. Here you have good old Sean Carroll, a mathematician, and this is what he's got to say about quantum mechanics after, 100 years, right, of this thing, right?
Quantum mechanics is weird because we still don't understand it. What is really going on in this, our best, most important framework for doing fundamental physics?
So here we are 100 years later, and they have no idea how quantum mechanics works. They have all the equations, they have all the descriptions, whether they're right or wrong, we don't care. The issue is, what's happening in that invisible world of subatomic world. And they have no answer for that. They don't know what's in there. Why? Because they're not visualizing. They're not dealing with objects. What they're doing is dealing with is mathematical concepts. And yeah, we have the problem with gravity, okay? The big unknown of quantum mechanics, right? And that's what they're still working on. It's got to do a little bit with the Higgs that we're going to talk about a little later. And, what is gravity? Well, gravity, like I say, just let go of the spoon. $1 billion experiment? No, just a 10-cent spoon. This one's a plastic one. You let go of it and it falls to the ground. And we know this. And so they haven't been able to answer. Not a single mathematician on earth can tell you what causes, why, this thing falls downwards, what the mechanism is. And there's only two possibilities. There's only two possibilities. Either something is pushing or something is pulling. That's it. This is kindergarten stuff. This is baby stuff. Okay? Something is either pushing or something is pulling. That's it. There's no other possibility. Okay, so the question is, is it pulling or pushing? Well, you have people like Richard Muller, and I've shown this in the past, but here's real quick. Every atom on Earth is pulling on every atom of you. You're also pulling on it. Okay? You're pulling on atoms right now on the other side of the Earth. Okay? And so it's pull, he's saying. Why does he say it's pull? Well, because of Newton's equation. Okay, here's the equation: mass divided by distance squared. That tells you that F, that's a force of pull. Mass is pulling on mass. It's not a push force. Okay, and people still have doubts, saying, no, we're going to do this with particles, and we're going to push it downwards, like pushing downwards. And a lot of these people don't subscribe to a theory that Mother Nature has ever invented pull. Okay? They say there is no pull. Mother Nature knows no pull. And so we have a problem with that because here, let me show you that Mother Nature has to have pull whether you like it or not. Okay? We have two magnets. Okay? And you can feel already that there's a pull from the inside. Nothing's pushing on my hands. I can feel already it drawing from the inside. Okay? So you got to explain the pull of magnetism, at least. Aside from, if you pull them in reverse, you have repulsion, right? But yeah, you have to explain the pull of magnetism. And so, yeah, there is pull. I'm sorry. And you have to explain pull. And in fact, you don't need to go to a magnet. You can do it also with gravity. If like he said, every atom on Earth is pulling on every atom of this spoon, we can understand why this is going down. And hopefully, you're not going to tell me that, the moon is pushing with particles or whatever it's sending to push this downwards towards the Earth. No, this is being pulled by the Earth underneath it. You still don't believe me. Okay, so let's go one step further. You put your arms sideways, okay, like this, right? Make a cross, right? And do that for 3 hours. And you'll find that, you have to struggle upwards against gravity, against the pull of the Earth, not against the push of the moon. And you still don't believe me. Well, then now turn upside down, do the same cross, but with your feet standing up. And now your arms are going to go down. You're going to have to pull against the pull of gravity, okay? So, yeah, you have to explain pull because gravity is a pull force, force of pull of some kind. And the only way you're going to be able to explain it is every atom in your body is bound somehow, physically bound to every atom on Earth. If there is no binding, if there's no mediator, no physical mediator between every atom of your body and every atom of the Earth, we have a serious problem because you're doing action at a distance, and that is the scientific term for black magic, for witchcraft. You're saying that there's nothing there, but somehow you're struggling against it. I'm lifting my arm against all the atoms of the Earth, right? They're trying to pull it down, and you're saying that there's absolutely nothing. There's ghosts and goblins, there's spirits. So there had better be a physical mediator, and of course you can see that you cannot see it. So you can't see the sea. You can't see the mediators of gravity and light. And so that's essentially, what the problem is. And so people who say, well, I can't see anything there, I can't touch anything there, so there's nothing there. And that's more or less the mathematical physics version of what things are, what existence is. Here you have good old Niels Bohr, and he says it to you in your face. He says, everything we call real, right, is made of things that cannot be regarded as real. Of course, he never defined the word real. Nothing exists until it is measured. He never defined the word exists. But his notion was that if you measure something, it exists. But if you measure and you can't find anything there, like, between the object, between the spoon and the floor, right? If you can't find anything in there, if you put your probe there and you can't find anything, you say there's nothing there. Nothing exists there because I can't measure it. That was his way of thinking, if you can call it thinking at all. So yeah, the main thing here is that there are invisible objects. There are invisible mediators, right, that Mother Nature uses. Not only invisible, but intangible. You cannot touch the mediators of gravity, and they are pulling on every atom of your body. And the issue there also is that, no one ever defined what real is, what exist means. You have atheists, agnostics, and theists going around in circles debating for centuries now about whether God exists or not. The issue was very simple, very, very simple. All you had to do was define the word exist. And if God meets the definition of the word exists, he exists pursuant to the definition. We're done, period. It's not a question of belief. Exist is not an issue of belief. And this is what these people thought. It was not only an issue of belief, but an issue of measurement. If I measure it, then it exists. If I can't measure it, it doesn't exist. Well, again, that's quite subjective, So, yeah, all these people, all they had to do all these years was define the word exist. And before that, you had to define the word object. And the word object is not that which you can see or touch, which is what Niels Bohr was essentially saying, that if I can't see or touch it, it ain't there, wrong. See and touch are not the criteria to define the word object. An object is that which has shape. It's a universal property. There is no object in the universe that does not have shape. And Mother Nature uses intangible, invisible objects to do her daily work. That's the end of that one. Okay, so let's move on to the Higgs. That's what we have to say about the Higgs. And the question is, what is the Higgs? Is this a particle? Is this a field? Because they talk about the field, and then they say, well, the field, the vibration of the field is what a particle is. But a field is a bunch of numbers, so they're vibrating numbers, and you say the vibration of a number, local vibration of a number, that's what a particle is. Not your classical corpuscle, by the way, not the one Newton was thinking about. He was thinking about little balls. And these people are saying, well, it's a vibration of a field, whatever that is. Okay, well, let's find out. If you want to know what the Higgs is, well, the best place to go is to the people who found it, and that's the people at CERN, the LHC. Okay, here it is. The Higgs boson. Okay, and what do they say? They say, you and everything around you are made of particles. Well, where did they ever get that? How did they ever prove that everything's made of particles? Meaning discrete little balls. That's what we're talking about here, okay? Because if the word particles means something else, like vibration of a field, then we're not talking about little balls. We're talking about something else, and that thingy is already in motion. In other words, it's not standing still. They're talking about vibration of a field, of excitation of a field, right? But when the universe began, no particles had mass. So we have two problems there. The first one is the universe began. What do you mean the universe began? What does that mean? How did it begin? Did time begin? Did space begin? Did matter pop into existence out of what? Out of nothing? What is nothing? What was there before nothing? The universe, I don't know. This sounds very much like, in the beginning in the Bible, right? And no particles had mass. Well, what is mass? Do we have a definition for mass? Turns out we're going to find out today we never had a definition for mass. We did, I guess, with Newton, but then that got thrown under the rug, swept under. And today we don't have a definition, or several, in fact. We'll see that in a second. And they all sped around at the speed of light. Why? Because they had no mass, right? So the photon is considered massless, just like the gluon, for example, which allegedly carries the strong force between quarks, right? And so what happened was, they said, all these particles, they had no mass until the good old Higgs came around and gave them mass. Stars, planets, and then life could only emerge because particles gained their mass from a fundamental field associated with what? The Higgs boson. Yeah, the bosons. And says the existence of this mass-giving field was confirmed in 2012. Wouldn't you know it? They always confirm these things that they need to create, a new cottage industry of something. In this case, the cottage industry of the Higgs, because now they're researching this stuff, trying to measure it and whatever. And they discovered it at CERN in 2012. So there you have it. That's in a nutshell, the history of the Higgs. They needed this Higgs particle for whatever, to give mass to other particles, and you wonder why the gluon, the gluon and the photon don't have mass. Why are they massless particles? I mean, don't they interact with a field? And it turns out that, the notion they give you this analogy of someone going through a crowd, and if there's a lot of crowd and you're bouncing around, well, you can't move very easily through the crowd, and that's a heavy particle. But there are others, that go right through the crowd. Like, they say if it's an important person, everybody wants to talk to them, ask for their autograph. Like the guy moves slowly, so he's got a lot of mass. And then the other person who nobody cares about, the bum on the streets, he can go right through. Nobody stops him. He goes right through. So he's massless. That's the analogy they give. They say that analogy is wrong. It's wrong. Why? Because they'd say it's not an issue of friction. You say, what do you mean? I thought that's what the point of the Higgs was, the Higgs field, that you have this particle going through this ocean, and this particle, for whatever reason, right, maybe it's big, whatever, it interacts, it, rubs against it. There's friction there between the particle and the field, and a massless particle like the photon, for whatever reason, doesn't have any friction with the field. They say no. It's a question of interaction. Well, what do you mean interaction? What kind of interaction? Is it touching it? Is it interfacing? Is there, head-to-head butting there or what? And they never explain that. They say it's the interaction. And the interaction apparently is long distance, action at a distance again. They never explain how a particle can interact without scraping its shoulder, without friction. And that's where part of the problem is. So here you have another notion from CERN. It says, what is the Higgs boson? Well, in our current description of nature, every particle is a wave in a field. The most familiar example of this is light. In other words, we have a particle, which is a wave, which is a wave, which is a field, which is a particle. So they go around in circles. I mean, is a wave the same thing as a particle? Especially if the particles go straight ahead, rectilinearly, and the other guys move up and down. You have a transverse wave or a standing wave, which have very little in common with straight line particles. But it says the most familiar example is light. Light is simultaneously a wave in the electromagnetic field and a stream of particles called photons. So it's both. It's a wave and it's photons. Take it or leave it, and you better take it because otherwise you don't get published. If you say that it's like me, that it's a rope, oh man, you get thrown out. Says, okay, in the Higgs boson's case, the field came first. The Higgs field was proposed in 1964 as a new kind of field that fills the entire universe. Fills the entire universe. How big is the universe? I mean, I thought it was infinite, or is it finite? I mean, what do you mean? Is the universe a container or some kind? Like your trash can, you put as much as you can in there, and gives mass to all elementary particles. The Higgs boson is a wave in that field. So the boson, I thought it was a particle. See, you look over there on the black square there on the right, you'll see the H, and which I circled there, and the H doesn't look like a wave like the one you see waving up there on the top. What you see is a little ball. In fact, they're all little balls with little signs on it. I guess the H is for Harvard or something. Anyways, the Higgs boson is a wave in that field, but they never put waves. I mean, maybe they should call it the standard model of waves instead of standard model of particles, right? Its discovery confirms the existence of the Higgs field. So yeah, they discovered it, they found it, done deal, give them a Nobel Prize, and we're done, right? Okay, so essentially, we have this field, whatever a field is, because a field is really a bunch of numbers, okay? That's all it is, a bunch of values. It's defined, the word field is defined as a value at each point in space. So we're talking about measurement that they made at different points in space. They have these values, they call the whole shebang a field. Okay, so We're talking about numbers. And the worst part is that all these numbers vibrate because, they don't stand still. They're changed constantly. So we have the changing of numbers. They call that a vibration. And they say that local vibration is a particle, a corpuscle, a ball, because that's what they represent it with, a ball. Okay, so it is a ball. If it quacks like a duck, walks like a duck, it better be a duck, right? So that's what it is. They put a ball. Well, it looks like what I see in front of me is a ball, right? Okay. Okay, so this is what the AI says, tells us again that the interaction is not resistance. It's not friction. It's an interaction, whatever that is. But they don't explain. You don't see there an explanation what they mean by the word interaction. What do you mean interacts? How does it physically interact? Does it bump against it? Does it touch it? What do you mean interacts? And how is it different interaction than friction? Okay, because that's how they really illustrate it. They show the particle trying to go through, a bunch of particles, and one has an easier time of it than another, right? In fact, here's where do I have it here? Well, I'll get to it in a second. But anyways, here's good old Sean Carroll again. He's going to tell us what other characteristics of the Higgs. Says fields can be bosons or fermions, right? But fermion fields kind of act like particle-like, right? They cannot pile on top of each other like boson fields. But fermion fields, there's only one kind of vibration at a time going on in the field. Okay, so it's like fermions cannot superimpose, well, boson fields, which carry forces, because that's what they are. They're force fields, right? It's like these force fields can go right through each other and nobody cares, right? Whatever those fields are, because again, you got all these fields are superimposed, they all act through each other. Nobody questions that. It's like, oh, it's okay because they're fields, right? And fields not a physical object unless you want it to be a physical object, which is when they want to turn it into a particle. But it says the fermion fields, there's only one kind of vibration at a time going on in the field. In any one region of space or any one quantum state, we can have as many bosons, as we like. But fermion takes up space, so you can only have one fermion there. Okay, fermions can only be one at a time. Okay, so you have to understand the difference. The fermions, since you have the big particles, let's call them big particles like protons and quarks and so on. And then you have the little, not the little particle because they're not really little particles. What they mean is fields. Okay? What they mean is fields, forces, or fields that carry forces, or forces that are made of fields, or any way you want to interpret that. And the point is that fields can go through fields, forces can go through forces, no problem. So you have the gravitational force together with the gluon field and photon field, and they all superimpose. Nobody cares. Nobody has an explanation for that. They just said they do because they need it mapped for the mathematics, not because physically there's something going on in there where really something is going through something else. But then when you get to the fermions, so the big ones, well, they collide. They can't essentially, occupy the same space. And that's not true either. Because electrons, when you do the slit experiment, you have the electron gun shooting a single electron, as they say, that they handle one electron at a time. It forks out, hits both sides of the two different slits, and then recombines on the screen. So they split it and they recombine it. So yeah, the electron does occupy the same space. So we don't know what they're talking about anymore because they have more contradiction, and even more contradiction over that. Okay, so he clarifies again. Carroll says the Higgs boson is not really a force-carrying particle. So it's neither this, neither that, but it's not really a fermion either. Okay, what is it? It's part of a field. That's what it is. It's part of a field that exists all throughout space, and the other particles are kind of swimming in it. Okay, so we have the little fishies, right? They're in the ocean, and they're swimming in this ocean, okay? So hopefully he's going to be talking about friction, right? Because the fish, they move through the ocean, and there's some friction between a fish and the water, right? The other particles, like the quarks, and the electrons and so forth feel the influence of the Higgs field, and it affects their properties like their masses and their charges. Okay, so the Higgs field is going to somehow affect them, but the question is, what is the interaction? I'm trying to find out, are they touching each other? Are they banging against each other? Is there friction there? And they say, no, there's an interaction. Okay, I'll take that as I don't know. Okay, so here's the Higgs field through the ether. Okay, my assessment of it, I'm saying the Higgs field is an ether, essentially, right? That's what they did. They reinvented the ether, just gave it a new name. The Higgs scalar field takes a non-zero value everywhere. Okay, so it's a non-zero value. Okay, so it's more than zero, right? Including otherwise empty space. The Higgs field permeates all of space. So I think what they're describing is the ether. And I just wanted to clarify that scalar is different than a vector, okay? Vector is a quantity with direction, whereas scalar doesn't have direction. So they're saying the Higgs field is not a vector field like electricity, for example. No, it's a scalar field. It doesn't have any direction, okay? It's like temperature, okay? And therefore, the Higgs scalar field is a bunch of particles, right? Existing everywhere at once and going nowhere. They're just there, right? It's this background of ether that they always had, right? The mathematicians have perpetually reinvented the ether, a background of vibrating particles, right? And given this space-filling ocean new names. And there you have all the different names they've had over time. Zero-point vacuum, the field, zero-point energy, quantum fluctuations, virtual particles, space-time, etc. And now they call it the Higgs field. They found the Higgs field. They proved it. They found a wave somewhere because they say the Higgs boson is really a wave in the field. So how do you find the field? I mean, can you draw a picture of that? Did you take a snapshot of it? How did you find it? How did you discover? How did you prove its existence? That's the question. And so if you want to know what the ether looks like, there it is. That's the ether. Okay, folks? Now you know what the ether looks like. And people don't like me putting that up there, but the question is, is the ether infinite? Are these particles infinite? Do they stretch forever and ever and ever like the universe? Is the universe finite, in which case it's a container and you have these particles in some kind of container? I want to know the shape of that container in that case, if it's finite, right? Then some people have these particles static without moving. Others have them moving, vibrating like you see there. And so they have these different ethers that they've invented over the centuries, and they just plug them in as needed. So they never defined the ether really well at all, okay, scientifically. And so today we have, the ether, but now it's called the Higgs, and people think they've discovered something new, the Higgs field. Okay, so what are the fatal errors with the Higgs field? Well, here, let me go through some of them. First of all, there are no explanations or understanding, right? They call that philosophy. They don't call it science. They don't call it physics. They call it philosophy. Meaning opinion. It's your opinion. And I have my opinion, so we don't care about that. Metaphysics is, let's drink some beer and find out what we did at the lab, what we got in conclusion. It's like, that's not important. And it turns out that everybody wants to know, for example, what gravity is. What is gravity? Okay, here we let go of the spoon, falls to the ground. People want to say, what caused that to happen? And not one of these people can answer it, but who do they go ask these questions to? They go ask the physicist, the mathematical physicist, who calls himself a physicist. That's who they go and ask. And the guy gives a lot of baloney about, equations and, the principle of equivalence, and goes through all this rigmarole, right? Bending of space-time and whatever. And you say, well, that doesn't sound very rational. Well, you're not supposed to take it literally. Well, but still, I'm trying to understand. You won't understand. If you want to understand, you got to go to philosophy, to metaphysics, to ontology. You're in the wrong place. Here, what we do is equations. So people are asking these folks, the mathematicians, tell me what gravity is, how gravity works, what is the mechanism, why is it doing all this stuff, why does everything fall to the floor? These people give them the runaround at the end. They tell them, by the way, it's not important because that's not what we do. We do equations. We do measurement. We do experiments, turn them into equations, and get Nobel Prizes. That's what we do. Okay, so now you know. Okay, so you're asking the wrong people. you're asking the wrong people. Don't ask a philosopher of physics, because they're going to ask the physicist, the mathematical physicist, what should I tell them? And the other guy said, well, we measured, and it's the bending of space-time. And that's what they tell them, it's the bending of space-time. That doesn't make sense. Yeah, we're not supposed to make sense of the universe. Father Universe does not have to agree with the way we think. That's the way they put it, the other way around. Father Universe doesn't agree with us. That's where the problem is. Okay, so we have physics, experiments, and math, like I showed, go to Galileo and Newton. All they did was experiments in math. That's what they thought science was. These are the people who started the mess we have today, why we have no explanations for anything, why we have a distorted notion of how the universe works or what exists out there. You have good old Sean Carroll. He tells us right out of the title of his presentation was "The Problem with Pretending Quantum Mechanics Makes Sense." I like that. You're not supposed to make sense of this, okay? You're just supposed to do the math, or like Niels Bohr said, shut up and calculate. That's how you do it, okay, in mathematical physics. And you have the field vibrating values. What is that? That's nonsense. You can't use the word field as a physical object and say, oh, I'm going to explain how the universe works with fields and energy and forces and mass. No, you can't, because those are not explanations. You cannot get a physical interpretation with those words. Those are mathematical words of mathematics, concepts, and you do not move concepts in physics. And then after 100 years, quantum mechanics doesn't make any sense, no meaning in there, and that's where they're all at today. They don't understand anything. They have equations, they have descriptions, but no explanations. Particle of mass, what's the problem there? Well, we have here the, the Wheeler. This is John Wheeler. And he says, he died now, and so did Taylor, right? Nature does not offer us any concept as the amount of matter, which is how Newton defined it. Here's Newton's notion of what mass is. The quantity of matter is the measure of the same arising from its density and bulk conjunctly. It is this quantity that I mean hereafter everywhere under the name of body or mass, and the same is known by the weight of each body, for it is proportional to the weight. Okay, so this was his notion of mass. Okay, he essentially said it's the quantity of matter, and that's the only definition that's not used today, the quantity of matter. They try to avoid that definition because it hurts them. Why? It hurts all of relativity. Relativity essentially has turned mass into weight. They said, how much is it? How fast is the thing traveling? Is it traveling at the speed of light? Well, it's pushing on the scale, right? So if we measure the mass, we would measure it speed of light pressing on the scale. And what is that? That's known as weight, not as mass. Mass is counting, not measuring, and that's another thing that Newton did not discover. And these people say, it's not the amount of matter. History has struck down every proposal to define such a term. Even if we could count the number of atoms or by any other counting method try to evaluate amount of matter, that number would not equal mass. Today, they have no idea whatsoever what mass is. Okay? And just in case, we check the Wikipedia, and what does the Wikipedia tell us? Well, that's even more shocking than what these two fellows told us. It says, in physical science, one may distinguish conceptually between at least 7 different aspects of mass, or 7 physical notions that involve the concept of mass. And there you have them. And the problem with all of them are measure. Mass is not a measure of anything. Mass is counting atoms, counting units of mass, which is in our theory is the hydrogen atom. You count the number of hydrogen atoms, you know what the mass of an object is. That's how simple it is. And it says inertial mass, active gravitational mass, passive gravitational mass. According to relativity, mass is nothing else than the what? Rest energy of a system. E equals mc squared. when there's no c squared. Curvature of space-time is a relativistic manifestation of the existence of mass. So these people say, well, mass is really curvature, geometry, right? So they have all these notions of what mass is. Nobody can tell you what mass is. And they stop, and I'll tell you why. It's because if they define mass, it's going to contradict one of the theories out there, especially relativity. You know, they cannot have quantity of mass, quantity of matter being mass. They need to have it the geometry of space-time, the curving of space-time. Time? You curve time? You bend a second? Or what are you doing there? So they have these irrational explanations. And if you define mass as it should be, like Newton defined mass, which is quantity of matter, he at least had the right notion, even though he said, I'm going to determine this through weight, by weighing it. That's where he failed. But the notion that it's quantity of matter, that was correct. That's what mass is. That's how it's different than weight. But today we have no difference between weight or mass, because you say, well, for example, we take the kilo, the old standard that we had for the kilo, one in France, the, what do you call it? The le grand kilo. And if you take that grand kilo to the moon, it weighs 1/6 what it does here on Earth. And you say, okay, the weight changed, but the mass stayed the same. And no, it also changed because the way we determine mass is by weighing. I mean, it's kilograms, right? You put it on a scale and you say, well, it weighs 1/6 on the moon as well, so it's got 1/6 the mass, until a mathematician can tell us the difference between mass and weight, you know. And the only way you can do that is by counting atoms. You can't do it by weighing, by measuring, okay? And that's part of the problem that we have with the Higgs, right? Why? Because the Higgs has all to do with mass and with gravity. That's what they're shooting for. They're trying to figure out the graviton, right? And before they can get to the graviton, they say, well, what is mass? You know, because mass is going to be pulled by the graviton, right? How did we acquire mass to begin with? And that's what the Higgs particle does. Okay, so here it says that the Higgs is a particle. Is that what it is, huh? And you look up the word particle, it says a small localized object which can be described by several physical or chemical properties such as what? Volume, density, or mass. Okay, that's a particle. So you look at the, what is a particle? It says it's an object, right? Because there you see it, localized object. What is an object? Well, it's a collection of matter. Okay, you look at matter. What is that? It's any substance. What is a substance? Unique form of matter. So you get this circular set of definitions, you know, and you never end up, you know, with a solid one that you can sink your teeth into. You know, a particle is an object. Object is matter. Matter is substance. Substance is matter. We're done. You went around in a circle. So we have a problem with all these definitions, which already is unhelpful. But then, you know, what are we talking about? What is the Higgs? What is gravity? You know, how does gravity pull on the Higgs? Because if the Higgs is, you know, in there giving mass to all the particles, including to the Higgs itself, you know, how does gravity have an effect on that? How are you going to make sense of all that? I mean, these people are talking about surrealistic theories here, right? And it gets only worse, because here you have good old Sean Carroll again. He's going to tell us that we know certain limits on what is possible. If you're an engineer, you might be a very, very clever engineer. You're not going to design a rocket ship that can travel faster than the speed of light. Physics puts limits on what we can do. In other words, he's saying nothing can travel faster than light, which comes from Einstein's special relativity. You know, he fixed the speed of light at 300,000 kilometers per second, and he started playing around with time and length and mass, all the other stuff, right? And so the speed of light is fixed. That's the yardstick, you know, that fixed yard, the constant, okay? And so he's right about that. He didn't know why, but he is right about that. And so here we have the situation where the tachyon, you know, is beating the hell out of the others. And you're saying, well, how is this possible? You have the photon is massless. It beats the Higgs, which has some mass. Why is the tachyon going faster than these guys? Well, the tachyon has negative mass, has has what do you call it? Negative energy, negative mass. It's imaginary energy, what they call. And so it delivers energy to the field, and therefore it can go faster than any other particle. You see how easy that was? That's why it can come from the future, from the past, or who knows from where. Tachyon beats them all. Okay, and why is this a problem? Well, because a minute ago we showed that you have the origin of the universe, like a picosecond right after the origin, after the Big Bang, right? Suddenly you have this Higgs field, because that's what's going to give mass to everything that comes afterwards. So they had to put it right at the beginning, 1 picosecond right after the Big Bang. But these people are saying that the tachyon field precedes the Higgs field. And you say, well, hold it, what are you talking about here? And here, let me show you. Okay, here you have the Big Bang, right? The Higgs field appears 1 picosecond after the Big Bang. Okay, and it says in the early universe, the Higgs field existed in an unstable configuration with an imaginary mass, meaning negative mass, right? In terms in its equation, a negative mass squared. Okay, so we have a negative mass now. A lot of women would like to have negative mass, right? At least take some pounds off. Now, at the end, you see the Higgs field itself is a tachyonic field in its unstable high energy state before the energy spontaneously converts into particles. Okay, so let's see what we got here. The Higgs field apparently is made out of particles, which, as we all know, are waves, right? And it's preceded by the tachyonic field, which has, some negative mass or something in there that we can understand. It's going to deliver this energy that turns into particles, which make up the Higgs field, okay? And now finally, all these particles can bump against, please don't say friction, okay? It's just interaction. They interact with the field, and this is how they gain their mass. Easy stuff. Ready to take the test on Friday? Okay, is anybody studying this nonsense called the faster than light? Well, I covered that the other couple of weeks. Let's go fast through that. Here you have the people who study the entanglement. Here's the people who study the warp drive. And why are they studying all this stuff? Because they want to go faster than light. They want to get out of a planet somehow to the other side of the universe, so they're looking at entanglement where you have to travel nowhere at all. You're already there because you're already connected to the other side of the universe. Warp drive, well, you got to go through the threshold from one universe to the other through the wormhole, right? Perhaps, or just have a rocket that, in this case, right, the warp drive that has a push from space-time from behind and a pull from space-time from in front. And that means you travel faster than the speed of light, okay? So they're working on the warp drive. You can see a lot of people are studying that, printing papers, right, on this nonsense, and you're paying for it. Here are the tachyons, right? Tachyons faster than light. Is anybody studying this nonsense? Yeah, of course they are. These people are heavy into, all this faster than light stuff. They're really into it. And of course, then you have the wormhole, okay, famous wormholes. Anybody writing papers on that? Yeah, all those papers are from this past year. So a lot of people are working on all this stuff. And the worst part is you're paying for it. You're paying these people's salaries, for them to work on nonsense, on tachyons, on faster than light warp drives, on wormholes. What is this? The world gone crazy or what? Is this physics? Okay, so we have here the LHC. It tells you what their goals are as far as the Higgs is concerned. Okay, can you do what can you do with 380 million Higgs bosons? Well, I don't know. There's got to be a lot of bosons out there. What is the fate of the universe? Why is there more matter than antimatter? Well, what lurks beyond the standard model? These are the questions these people are investigating. Are you surprised that they're shutting down the LHC? I hope they do. I hope they never bring it back up again. These people are studying nonsense. Now here's the AI. The AI tells us what these people are really studying. Okay, in more detail, it says detailed measurement of the Higgs bosons, properties and interactions to determine what the mechanism by which elementary particles acquire mass. I thought they knew what the mechanism is. And that's what they're referring to. They're referring to that interaction, which they've never explained. They say it's not a friction, it's an interaction, whatever that is. So they're trying to figure out the mechanism now. I thought they had the mechanism. I thought before you can go into math and do equations, you better have the mechanism first. You better visualize, what you're trying to describe mathematically. This is not what they do. They don't have a mechanism. They don't have a mechanism of interaction. They say it interacts. And you say, well, that sounds like friction. Well, it's not friction. It's just an interaction. Okay, whatever that means. Search for evidence of dark matter. That's got them crazy. The dark matter is the stuff on the outside of galaxies that makes the stars on the outside of a galaxy travel faster or as fast as those on the inside. They're trying to figure out what this dark matter is, which ain't there. It's just they're looking for ghosts and goblins and spirits. They're trying to measure that. Candidates, what are they? The WIMPs, the weak interacting massive particles. So they have these massive particles that interact weakly with matter. Whatever that means. Okay, what do you mean weakly interact? They either touch or they don't touch. It's black or white, not weakly. Okay, and then they have others that are hidden from the particles from the hidden sector. They're searching for missing energy in the detector, and they think that again, they find an equation where they miss a little bit of value there, a little bit of energy. They give it a name, and they say, "Oh, we found another particle," and they just give it a name. They'll call this one Johnny, the Johnny particle. Then you have the discover new physics. That's why they're doing all these experiments, that maybe they can find some new physics, whatever that means. To answer why there is more matter than antimatter in the universe, or how gravity fits in with the other forces. That's what they're doing. That's what you're spending money on the LHC, on CERN, SLAC, stands for Linear Accelerator Fermi Lab, Brookhaven Laboratories, Michigan. They have all these places where they have these accelerators. What are they doing? They're just hitting what they think are discrete particles. They can't see in there. So they just look at the results. They see, we see some traces here in the medium. They take pictures of those. Really, they do computer simulations. They do, of what these traces are. And then they look at the traces and say, here's a particle. Here's another particle. This one went right. It's positive. This one went left. It's negative. Whatever that is. That's all they is. So they give names. They give charges. They say this one has so much mass, and they say this one's negative, that one's positive. That's it. And if this one's the positive one, that one's the antiparticle. And that's how they do all this stuff. It's just called, stamp collecting. That's what we call it. Okay, so are you paying for this? Well, here's the U.S. budget for the Large Hadron Collider. Provided significant funding for the construction of the Large Hadron Collider, LHC, contributing over $500 million. I wish I could use that money, right? Through a 1997 agreement, primarily for components and detectors, with the National Science Foundation, right, and Department of Energy funding. While this was a major construction contribution, current U.S. support also involves funding for what? U.S. scientists, they call them scientists, right? And institutions that conduct research, operate detectors, and process data at CERN. They should not call it detectors. They should call them operate defectors. Defectors. I like that better. Would sound better in there. So you're paying for it. Yeah, you're paying for it. And, is anybody writing papers on the Higgs? Well, here, a bunch of papers. Collected again, only 12. That's all that fits on the page without bothering you too much. And these are from last year, and there's a bunch more. So everybody's investigating the Higgs. Everybody's investigating dark matter, tachyons, wormholes, all the garbage that came out of quantum mechanics and general relativity, not to mention string theory. Okay, so what are some of these papers? Well, here I pulled out a few. What are these people into? What are they trying to? What are they working on? What are they trying to prove, or what are they writing about? I mean, these novels or what? It says Higgs pair production, gluon fusion. It says Higgs pair production offers the opportunity to probe correlations among couplings of one or two Higgs bosons, two fermions and gauge bosons. So we have a lot of boson studying here. Another one says, in regions of extreme gravitational intensity, such as near gravitational singularities, space-time and the Higgs field engage in a dynamic interplay that extends space-time beyond the singularity. Okay, so we have singularities that's in infinity. That's all it is. When they encounter an infinity in math, they call it a singularity, and that has very little to do with physics, a lot to do with math, right? And here we have another one that says, we investigate the role of the Higgs field as a fundamental scalar, not vector, right? Not the vectorial, but scalar in the Standard Model within the framework of modular inflation models, where a modulus field acts as the inflaton, remember what happens is you have this Alan Guth, and he came up with a notion that there's an inflation period right after the Big Bang, and they're saying this was due to the Higgs. That's essentially what these people are investigating. Then you have another one, a comparative study of Higgs event classification at the Large Hadron Collider that bypasses the traditional reconstruction chain, whatever all that means, right? The survey of rare and exclusive few body decays of the Standard Model, Higgs boson, defined as those into 2 to 4 final particles with branching fractions. This is what these people are doing. They're just doing equations out there and simulations on computers. That's all they do. Top quark decays are sensitive probes of light-charged Higgs bosons due to sizable, and they put these values there, right? Production cross-section at the LHC in conjunction with their distinct experimental signatures. Okay, so they're comparing experiment against their theoretical values, I guess. That's what they're doing. And another one, a scenario where the sole Standard Model Higgs is responsible for reheating the universe. We're heating the universe, okay? After inflation. Again, they're looking at this right after the Big Bang. That's what they're trying to show. They're trying to predict what happened in the past, right? Produces a significant background of gravitational waves and maintains the full classical stability of the electroweak vacuum. Electroweak vacuum. What in the world could that possibly be? Electroweak vacuum. And yeah, it's exhausting because all these people are just doing a lot of equations and simulations on their computers, and then they write papers, they get published, and they're not interested in the nonsense that they write because nobody reads that stuff. It's, hey, how many papers did you write? I wrote one, publish or perish, so they publish just so they won't perish, and they keep their name afloat, then they can put it in their in their resumes. Look at all the papers I published with so-and-so, with Charlie, with Johnny, and all these people. So they put all these papers they got there to see if they can get a job, like at CERN, at SLAC, or any of the accelerators, or maybe in a higher level institution like the advanced studies in Princeton or whatever. So this is what they're into. They're into making a career for themselves. The nonsense they're writing is not even worth reading. It's just nonsense. They just want to show that they know how to do calculus because I wrote a paper. See, and here it is. Here's the calculus that I did, and see, I'm not so dumb as you think I am. Okay, so that's what it's all about. And so let's end this with a good note here. Okay, let's end it with a good note. Here we have good old Einie. Okay, and he came up with this equation. That was in, I think, his his second paper in 1905, the Annus Mirabilis year where he wrote 4 papers. And he said energy equals mass times velocity of light squared. And people say, well, what does that really mean? I mean, physical terms. Well, here we have a couple Nobel Prize winners and prominent people who will tell you. You have Richard Feynman. He says, it is important to realize that in physics today, we have no knowledge of what energy is. Of course, good old Rich, he didn't know that energy is not a what. It's not a thing. Energy is a concept. And so he confused it for a thing. And so he's saying, I don't know what it is. And then he spoke hours about energy as if he knew what it was, right? No, energy is not a what. And there you see it's a concept. It's called the capacity, the ability. That's what it's how the word energy is defined. Okay, and then on the other side, you have what I showed earlier, John Wheeler and Edwin Taylor, and they say, look, we don't know what mass is, and it's certainly not the amount of matter. And Wikipedia says what? That you have at least 7 different notions, definitions of what mass is. So we have no idea what mass is. We have no idea what energy is. But Einstein says that E equals mc squared. Energy is equal mass times velocity squared. And so I came up with a better definition, better equation, okay? And you can take this one to the bank. This one's for real, okay? And here it is. Drum roll, please. There it is. And it's L equal I C squared. And you say, well, what does that mean, Bill? Well, it's straightforward. I mean, L is love and I is intelligence. So L is equal to intelligence times velocity of light squared. Now, you say, well, Bill, what is intelligence? Well, we don't know what intelligence is, like we don't know what mass is. We don't, and I don't think there's a single person on earth that knows what love is. I mean, you know, men are attracted by women, women are attracted by men, most of us. And that's what love is. We just have this notion of what love is, and what intelligence is, nobody knows. So I think I'm in my right, just like they are in their right, saying that E equals mc squared, L is equal to I c squared. And I do c squared